Hello, welcome to another module in this massive open online course on the principles of CDMA, MIMO, OFDM wireless communication systems. So, in the previous module we have seen various aspects of MIMO communication systems, the properties, the behavior and the various transmission schemes and the analysis related to MIMO communication systems. Let us now in this module start with a new technology, that is OFDM. So, what we are going to look at in this module is, that is starting with this module, is introduction to a new technology and in fact a very prominent and a very key technology, that is OFDM, which stands for orthogonal frequency division multiplexing. So, we are going to start with OFDM, which stands for orthogonal frequency division multiplexing, and this is a key standard because OFDM is employed in 4G wireless systems. So, this is a key technology which is employed in 4G wireless, that is the 4th generation wireless systems, such as if we look at for instance LTE, this is a 4G cellular standard, this is a 4th generation cellular standard, and this stands for long term evolution, correct. We have already seen this. Another 4G or 3.75G standard is WiMAX. As we have seen, this stands for world wide interoperability. For microwave access, that is worldwide interoperability for microwave access. So, we have LTE, which is long term evolution, which is a 4G cellular standard, and another competing standard which is WiMAX, worldwide interoperability for microwave access. Both of these are based on, these are dominant standards, and both of these are based on OFDM. So, if we look at the cellular world, both of these are based on OFDM. Similarly, LTE advanced, that is denoted by LTE-A. So, if we look at LTE-A, that is LTE advanced, which stands for LTE advanced, this is also based on OFDM, which is orthogonal frequency division multiplexing. So, OFDM, what is the important aspect of OFDM? OFDM is a key broadband wireless technology. So, this is a key wireless, and we can emphasize broadband wireless broadband technology, and by broadband we mean a system, basically a wireless system which has a large bandwidth. So, this wireless system supports a large So, what are we looking at? We are looking at OFDM, which is orthogonal frequency division multiplexing, which is a key wireless technology, and not just that, it is a broadband technology. So, it operates on a huge bandwidth, it operates on a large or a very wide bandwidth. For instance, if you look at a GSM system has a bandwidth of about 200 kilohertz, but an OFDM system can have a bandwidth up to 20 megahertz, right. So, this is several times that of, for instance, this is about 100 times that of a GSM system. So, it operates over a large bandwidth, it is a broadband system. Since it has a large bandwidth, therefore, naturally the data rate is higher, and these high data rates are used in 3G and 4G, in fact 4G wireless systems to enable data rates up to hundreds or even more than 100 megabit per second, about 500 megabit per second or even up to 1 gigabit per second. So, LTE and LTE advanced, which are based on OFDM and operate thereby, our broadband wireless cellular system can support, can enable a very high data rate of the order of hundreds of megabits per second. This is possible because of OFDM, which stands for orthogonal frequency division multiplexing. And not simply cellular standards, but if we look at Wi-Fi or wireless LAN standards. So, several Wi-Fi or wireless LAN, that is wireless local area network standards. So, these are wireless Wi-Fi or wireless local area, WLAN wireless local area network standards. So, these WLAN standards, what are the various WLAN standards? For instance, 802.11a, 802.11g, 802.11n, and the more recent 802.11ac. If you look at all of these are the various IEEE WLAN standards. So, these are IEEE WLAN standards, and these are based on, these enable high data rates because these are based on OFDM or orthogonal frequency division multiplexing. So, several wireless LAN standards such as 802.11g, 802.11a, 802.11n, 802.11ac, which are the Wi-Fi standards. Colloquially, these are known as Wi-Fi standards, where technically these are wireless LAN, wireless local area network standards. These are also based on OFDM. So, OFDM is a key wireless technology which is used in several cellular, 4G cellular and several wireless LAN standards, because it is a broadband wireless technology which enables high data rates. At the same time, it has a low complexity of implementation. It enables easy implementation of these broadband wireless communication systems. So, let us look at the basic principle of OFDM. So, what is the basic principle behind OFDM? And the basic principle behind OFDM can be explained as follows. The basic principle of OFDM can be explained as follows. For instance, if you look at a typical communication system, a communication system, as we all know, has a certain bandwidth which is B. I have a communication system over a bandwidth which is B, and I have a single carrier. I have a carrier. So, in a communication system, I have a bandwidth and I have a carrier, a single carrier placed at the center of the bandwidth at the carrier frequency, correct. So, let us say this is our carrier frequency. I have a single carrier. Let us take a simple example. Let us say my bandwidth is 10 megahertz. So, this is a broadband system. So, this is a broadband system of bandwidth 10 megahertz. Now, therefore, if we are performing communication, the communication system that is implemented over this bandwidth has a symbol time t is equal to 1 over the bandwidth B, and 1 over the bandwidth B, we know bandwidth B is 10 megahertz. So, this is 1 over 10 megahertz, which is basically 1 over 10 into 10 to the power of 6 hertz, which is 0.1 into 10 to the power of minus 6 seconds equals 0.1 microsecond. So, therefore, we have a symbol time. That is what we are saying is we are considering a communication system which has a bandwidth of 10 megahertz. In this bandwidth B, which is 10 megahertz, the symbol time is T equals 1 over B. Therefore, the symbol time is 1 over 10 megahertz, which is 0.1 microsecond, right. So, what we are saying is for communication over this bandwidth of 10 megahertz, the symbol time is 0.1 microseconds. However, you might remember from the initial modules, that is the delay spread. If we look at a typical outdoor channel, the delay spread of the wireless channel is approximately 2 to 3 microseconds, that is 2 to 3 microseconds. So, if I look at TD, where TD is my delay spread, TD is approximately of the order of 2 to 3 microseconds, which means now if I look at the relation between this symbol time, now let us look at this, our symbol time is 0.1 microseconds, our delay spread is approximately let us say 2 microseconds. Therefore, the symbol time T is much less than what we are observing is the symbol time T is much less than the delay spread. The symbol time T is much less than the delay spread. What we are observing is the symbol time is 0.1 microsecond, the delay spread is about 2 microsecond. So, the delay spread is about 20 times larger than the symbol time, correct, which means now you might also remember from the characteristics of the wireless channel that when the delay spread is larger than the symbol time, we have inter-symbol interference. So, this, what does this lead to? This leads to a problem. What is the problem? This leads to ISI or what is also known as inter. So, what we are observing is as the bandwidth B increases, as bandwidth B increases, what happens is our symbol time symbol time 1 over B decreases, correct, and therefore, as the bandwidth, so the system becomes more and more broadband, that is the bandwidth B is increasing, it is becoming larger and larger, the symbol time 1 over B is becoming smaller and smaller. Now, since the symbol time is becoming smaller, it is going to become lower than the delay spread of the channel. Once it is lower than the delay spread of the channel, this results in inter-symbol interference, and when you have interference, this leads to a degradation or this leads to a loss of performance of the wireless communication system. So, the inter-symbol interference resulting in a broadband wireless communication system leads to a performance loss, leads to a degradation of the performance, and therefore, this is a significant challenge, this is a significant problem, and addressing this problem of inter-symbol interference is a significant challenge in a broadband wireless communication system. So, this leads to inter-symbol interference, leads to ISI, as we said ISI stands for inter-symbol interference, and this is a significant challenge in a broadband this is a significant challenge in a broadband. This is a significant challenge in a broadband wireless system. So, how to overcome ISI? So, our main problem is to overcome the intersymbol interference. What is the challenge? The challenge is to overcome the intersymbol interference. The challenge is basically because of this small symbol time, that is, as the bandwidth is increasing, the symbol time 1 over b is decreasing, which is leading to intersymbol interference. The challenge is to overcome this intersymbol interference. And what is the principle, what is the method or the means to overcome this intersymbol interference? And the scheme is simple. How to overcome the intersymbol interference? So, and the principle to overcome, that is to avoid intersymbol interference. Realize that the intersymbol interference is arising in the first place because of the large bandwidth. So, what we do is, when we have a large bandwidth, instead of using the entire bandwidth at once, what we do is we use it piecemeal. What we do is we take this large bandwidth B and we split it into smaller bands, or we split it into what are known as sub bands. So, I have a large bandwidth which I said is 10 megahertz. I am splitting this into smaller bands. So, I am splitting this into each smaller bands which are termed as sub bands. So, previously we had a single carrier. Now, we will have multiple carriers, one in each sub band. This is termed as a sub carrier. So, we will have smaller sub bands. In each sub band, place a sub carrier. Now, if you look at this, if I let us say have n sub bands, I am saying smaller sub bands, let us say n, right, then bandwidth of each sub band is equal to B by n, correct. So, what we are doing is we are taking a large bandwidth B, we are dividing it into n sub bands. So, the bandwidth of each sub band is B by n. Let us take a simple example. For example, B equals, let us say 10 megahertz and n equals 1000. What is n? N is basically equal to the number of sub bands is equal to 1000, then the bandwidth per sub band of each sub band, bandwidth of each sub band is equal to B by n, which is equal to 10 megahertz divided by bandwidth of each sub band is B by n, which is 10 megahertz divided by 1000, which is equal to 10 into 10 to the power of 6 divided by 10 to the power of 3, which is equal to 10 into 10 to the power of 3, which is equal to 10 kilohertz. So, the bandwidth of each sub band is equal to, so bandwidth of each sub band. So, we are taking a bandwidth B of 1000 of 10 megahertz, we are dividing it into 1000 sub bands, bandwidth of each sub band is 10 megahertz divided by 1000, that is 10 kilohertz. Now, if you look at the symbol time in each sub band, now therefore, symbol time in each sub band is equal to, the symbol time is 1 over B over N is equal to N over B. That is, in our example, symbol time T becomes 1 over 10 megahertz divided by 1000, that is basically, as we have seen, 1 over 10 kilohertz, which is equal to 1 over 10 into 10 power 3, which is basically 0.1 millisecond, which is equal to 100 microsecond. Now, if you look at this 100 microsecond, now if you look at this new symbol time, which is 100 microsecond. So, now let us look at this new symbol time, which is 100 microsecond, and compare this now again with the delay spread, which is 2 microsecond, and now you can see that T is much greater than the delay spread, that is, we have 100 microseconds is much greater than 2 microsecond, that is new symbol time, the new symbol time is much greater than and therefore, now what we are seeing is basically the new symbol time is 1 over B by N, that is 1 over the bandwidth of each subcarrier, and the bandwidth of each subcarrier is 10 kilohertz. So, the new symbol time is 1 over 10 kilohertz, which is 0.1 millisecond or 100 microseconds, and the delay spread is 2 microseconds. So, the new symbol time, which is 100 microsecond, is significantly greater than the delay spread. Therefore, there is no inter-symbol interference in this system where you are using multiple sub-bands and multiple sub-carriers. Therefore, the usage of these multiple sub-bands and sub-carriers, therefore, this means there is no ISI in new system, in the new system with multiple sub-bands and sub-carrier in each band. Subcarrier in each band, such a system with multiple. So, such a system with multiple sub bands and a subcarrier in each band. So, what are we doing? We are taking bandwidth B, dividing into n sub bands. In each sub band there is a subcarrier. So, there are n subcarriers. Such a system with multiple sub bands and multiple subcarriers is termed as a multi-carrier system. So, such a system with multiple sub-bands and multiple sub-carriers is termed as a multi-carrier modulated. Multi-carrier modulated system. So, this is known as an MCM system, which is basically a precursor for OFDM. So, what we are seeing here is that we have a multiple sub carriers, we have multiple sub bands, and in each sub band we have a sub carrier. Therefore, we have multiple sub carriers and we are modulating these multiple sub carriers. Such a system is known as a multi carrier or multiple carrier modulated system, that is an MCM system, and this is the basis for OFDM. This is a precursor or basis for OFDM. This is not exactly OFDM, this is a basis for OFDM. So, what is OFDM? OFDM is basically a multi-carrier modulated system, that is where we have multiple sub bands and multiple sub carriers, each sub carrier representing a small sub band, and since the bandwidth of each sub band is small, therefore, the symbol time is large. Once the symbol time is large, the symbol time is larger than the delay spread, therefore, there is no intersymbol interference or negligible intersymbol interference in each sub band, and this enables transmission, this enables smooth transmission and smooth reception in a broadband wireless communication system. So, that is the principle behind MCM, which forms a basis of OFDM, that is orthogonal frequency division multiplexing, and we are going to explore this idea in greater detail in the subsequent modules. Thank you very much.